Okay, hello everyone. So this is lesson 3.3 all about homogeneous linear equations with constant coefficients. Okay, so by now we know that there are different techniques to solve different um, classifications of differential equations. Okay, so for this particular classification, we are going to use the auxiliary equation method. Okay, so let's start with a first order equation. So we have here let's say a y prime plus b y is equal to 0. Okay, so where a and b here are both constants. Okay, so if we examine this equation, let's say if we manipulate it a bit and let's express y in terms of y prime. So we transpose as if we subtract ay prime from both sides, we will get negative ay prime here. So dividing both sides by b, we get negative a over b y prime. Okay, so a over b here, a and b here are basically constant, so we can express this as c, right? So we can then say y is equal to c y prime. Okay, so we see here that y and y prime are constant copies of each other. Okay, so in order for this to be satisfied, we need to have a very special type of function. So the function that can satisfy this is actually the natural exponential function, which is y is equal to e raised to mx. Because if we take the first derivative of this, we will get m times e raised to mx, right? M is constant here. Okay, so now that we know that this is the general form of our solution, so this is a very special function. So let's erase it first. So now that we know that the form of the solution is y is equal to e raised to mx, and y prime is equal to m e raised to mx, we can substitute it back to our original equation and get a multiplied by m e raised to mx plus b multiplied by e raised to mx is equal to 0. Okay, so if we factor out e raised to mx, we will get am plus b is equal to 0, right? And since e raised to mx, so this is the natural exponential function, we know that this can never be equal to 0, right? Because if you take a look at the graph of the exponential function, we will see that um, the curve never intersects the x-axis. Okay, so in order for this equation to be true, then in order for the statement to be true, then am plus b must be equal to 0. Now, this equation right here is actually our auxiliary equation. This is our auxiliary equation. Okay, really cool. Okay, so if we try to solve for m, you'll get m is equal to negative b over a, right? So, now that we have our value of m, we can then say that the general form of our general form of the general solution is y is equal to c, say c1, e raised to negative b over a x. Okay, so this is negative b over a in place of our m. Okay, so this is our general solution. Okay, okay, so let's apply it to an example. So we have here example 1. So actually, we only have one example for this. Okay, so we know that the general form of our solution is y is equal to e raised to mx, right? So let's substitute it to our original equation. So and y prime again is equal to m times e raised to mx. So 2 multiplied by m e raised to mx, right? Plus 5 times e raised to mx is equal to 0. Sorry. So if we factor out e raised to mx, you will get 2m plus 5 is equal to 0. Now again, this statement is to be true, then 2m plus 5 should be equal to 0 because e raised to mx cannot be equal to 0. Then if we solve for m, you will get m is equal to negative 5 over 2. Okay, so our general solution therefore is y is equal to c1 e raised to negative 5 over 2 x. Okay, so this is now our general solution. Okay, so in the next video, we will try to apply this methodology to second order equations, and in the latter videos we will apply it to higher order differential equations. Okay, so thank you for watching and I hope you learned something in this video. See you in the next one.